Now, we use the complex notation for vector amplitudes of this vectorial wave, where E of RT is E naught exponent I k dot r minus omega t, right? So we now have the same plane wave solution, but now the tildes represent the fact that we have used a complex notation. Just have a sip of some warm water to get my throat in order. So E naught has an X, Y, and Z components, with all of which are complex numbers. So we have real and imaginary numbers. So real part of the X component is real X, real E naught X plus imaginary part of E naught X, real part of E naught Y plus imaginary part of E naught Y, real part of E naught Z plus imaginary part of E naught Z, right? So in total, we need 6 real numbers to describe this electromagnetic wave in its complete form. However, considering the fact that light waves are transverse, 2 of these components for the transverse wave would be set to 0 if the wave propagates along one of the directions of the coordinate system. Typically, we have been choosing Z to be the propagation direction, so we wouldn't have any finite non-zero valued electric field along the Z direction. So if the wave is propagating, a light wave is propagating along the Z direction, we essentially have non-zero values for X and Y components. In fact, yeah, in cases like circular polarization, you cannot eliminate either of these to be even one of the 2 other components to be 0 always. Okay, so we then considered the superposition of light waves. So if E1, and E2 are solutions to the wave equation, I mean, please excuse the fact that my vector signs on R have moved out somewhere, and there's a script E here instead of the regular E. Let us treat them all to be equal. So if we have 2 solutions, E1 and E2 to the wave equation, then the sum of the 2 is also a solution. We proved this rigorously in one of the previous lectures. So let me ignore going through this proof in detail. And what did this mean? In terms of a picture, you take a region of space, where region of interest in space, and a wave one wave, say E1, propagates in this sort of up to down direction, and it is crisscrossed by the wave E2 so that they overlap and occupy the same volume of space. Waves can do that. That is exactly what the fact that the sum of these 2 waves also solving the same wave equation means. The same wave equation as the individual waves solved by themselves. So this essentially means that they can coexist in a region of space. Not only that, we still have the individual identities of waves E1 and E2 in another region of space where there is no overlap owing to the fact that these 2 beams are finite. You should have the wave E2 or the wave E1 present or coming out of this interaction region in the same form as they would have without the other being present, which is to say that superposition principle always holds. So if I can look upon the wave E2 as a 0 constant E1 wave plus E2, so this wave would have survived, would have been just as well as it is. E1 is essentially E1 plus a 0. Now, if I changed the wave from the E2 wave from being 0 to some other finite value, E1 should still remain the same, because this principle holds in all its generality. Okay, so therefore they can occupy the same volume in space and overlap with each other, yet not affect each other's condition or whatever be it, right? So if they emerge from a region where they interact out, the waves remain intact, provided the medium is lossless and as ideal as we are making it out to be here, right? So in this idealized scenario, both these waves will interact and remain sort of untouched by each other. Now, irradiance is what we measure of waves. We saw that. in the earlier lecture. It is essentially the dot product of the electric field amplitude with itself. So E naught dot E naught star. So the irradiance of a wave essentially, if both these waves are proportional to e to the I k dot r minus omega t, then the irradiance is 1/2 c epsilon E naught dot E naught star. This is 1/2 c epsilon E naught x star plus E naught y star plus E naught z star, right? So what does this mean? I'm basically taking the complex conjugate of each component and multiplying it with its partner component and then adding up the entire thing, right? So we considered two cases, the case of the two waves which are being superposed here, let's say E1 and E2, having polarizations along two orthogonal or perpendicular directions, which we can say are x and y in our coordinate system for a z propagating wave. In this case, when the polarizations of these two waves are perpendicular to each other, right? So then note here, we are doing a dot product. Okay, so there is a sort of cos theta term that is involved in these dot products, right? So we have here for the irradiance a 1/2 c epsilon E naught x star plus E naught y star, right? So the wave 1 was polarized along the x direction. So this first term corresponds to wave 1, whereas the second term corresponds to wave 2 over here. So as a consequence, this is wave 1, this is wave 2. Now, it turns out that if the waves have two different polarizations, then the irradiance or intensity of the summed up wave in the region of overlap essentially is the total irradiance is the sum of the two individual irradiances. Nothing interesting seems to be happening here, okay? But then let's turn to the other scenario where the electric fields E1 and E2 corresponding to these two waves essentially are both along the x direction, okay? So now if the two waves have their polarization along the x direction, it simply means that the electric field values for the y and z components are both identically 0. Now let's compute the irradiance as we did earlier, and here we get three terms. The first term has E1 dot E1, the last term here has E2 dot E2, and we have an interesting term in between, which is a mix of E1 and E2, which we call the cross term. And this is where all the magic happens. So when two waves have the same polarization, we begin to see this very iconic phenomenon of optics called interference. Okay, so this is an important facet of the of optics, and essentially this is, therefore you can say that a condition for observing interference is that the two interfering waves have the same polarization. Okay. Now, let's look at this sort of pictorially. The condition where we have two different polarizations, okay, again in terms of two waves sharing a region of space and intersecting with each other, there is an overlap region of space here where they crisscross each other. So here, this is corresponding to what I discussed earlier. Now let's take the same scenario for the case of these two polarizations, the polarizations of the two waves E1 and E2 being along the x direction. Then, although the k vectors can be different, so the propagation vector in this case points a little upwards. In the second case, the propagation vector points downwards. Now, in the case that we have the polarizations to be the same in the overlap region, we don't have a simple addition of the two irradiances or intensities as it was in case one considered here on top. We have here something more happening owing to the interference term. We start seeing the so-called fringes of interference. Okay, so we will quickly see why these fringes come about. by considering the details of this interference term, which is the real part of E1 dot E2 star. Now, we want to consider a particular scenario where E1 and E2 are of the following type. The wave E1 has an electric field as shown here. It is essentially E naught, the amplitude, multiplied by I omega t. Whatever happened to the kz, I'm deliberately considering the point z is equal to 0, okay? Or z is held as a constant, so I'm ignoring it for the moment, but treated that I'm considering this at the point z is equal to 0. The point z is equal to 0 actually constitutes a plane if it were to be the Cartesian coordinate system under use. For the second wave we have for E2, we have this to be E naught exponent of I omega t minus tau, where tau is a time delay. Tau has units of time. Tau here is not the cyclical, not the time period of the wave. It could be any delay value. Okay, so let us consider this hypothetical situation where the amplitude of the wave is identical, but the two waves are simply delayed by a small amount of time tau, and compute the irradiance of these two waves interfering or overlapping in a region of space. Okay, with this time delay tau in between them. The total irradiance turns out to be the following. It is essentially I is I1 plus I2, but I1 and I2 are identical. They are the same. So, and they're also equal here to I naught, the individual irradiance of each wave. I naught here is what? It is just 1/2 C epsilon E naught square. That's it, right? 1/2 C epsilon E naught square. So this is twice I naught. Okay, I1 plus I2 is twice I naught. And then we have the interference term. What is the interference term? The interference term is C epsilon, real part of E1 dot E2 star. Okay, so E1 multiplying E2 star is E naught exponent of I omega t, multiplying E0 star or E naught star, exponent of now minus I omega t minus tau. Okay, it is just the I becoming minus I in this expression owing to the complex conjugation. Okay, so this now imposes a mathematical simplification where the terms containing the t cancel out. They both have opposite signs. And we are simply left here with E naught star, that is absolute value square of E naught, multiplying now the exponent of I omega tau, where tau is a delay. Okay. So now, what is the real part of absolute value square of E naught exponent I omega t? It is just absolute value squared of E naught multiplying cosine omega t. Tau is a delay. So you can have a knob on the delay, tau by yourself, and tweak the delay. That's what the idea of this exercise is, right? But before we do all that and tweak, let's realize that I naught was 1/2 C epsilon absolute value square of E naught. So since that is the case, we essentially have here I to be twice I naught plus twice I naught multiplying the cos omega t term. Okay, cos omega t can take values between -1 and +1. Okay, so as a consequence, when cos omega t is -1, you can have 0 intensity, 2 I naught minus 2 I naught. Whereas when cos omega t is +1, you have 2 I naught plus 2 I naught. So you can have maximum intensities which are higher than the sum of the individual intensities I1 plus I2, or in this case, I naught plus I naught. So now, but all that depends upon what the value of tau is, because omega is a fixed feature of the wave, the angular frequency. Okay, so let me plot this resultant expression, the summed up irradiance as a function of tau. You of course guess now that it should be a sinusoidal function, because tau is varying and the intensity is flopping between a minimum 0 and a maximum 4 I naught here. So now, if I were to view this on a screen, the maximum would look like a stripe. The minimum would look like a dark stripe. The maximum would be a bright stripe, dark stripe, bright stripe, dark stripe. So these stripes are called fringes. So we have bright fringes and dark fringes. I'm not making this specific to any particular experiment. You would of course be, alluding to, if you have done a course on optics, to the so-called Young's experiment or any other, maybe an interferometer of some sort, right? So, but then those are all manifestations or realizations of creating this delay in some way, okay, and creating this fringe pattern. So the fringe pattern will always come up so long as you have the same polarization. And now we realize even the same frequency for the two interfering waves. So this leads us now to a new concept which we have not introduced into this course so far, but is nonetheless quite important, which is the concept of coherence, right? Coherence, in some sense, is a measure of the observability or the visibility of the interference phenomenon. Okay, so now we have a nice little table over here, where on the going from left to right on this table, we have two possibilities. We have a case where the polarizations of the two waves are the same. The second option is that the polarizations of the two waves are perpendicular. It's not that they are not unidentical alone, they must be perpendicular. So we are considering two extreme polarization geometries for these two waves, right? Then on the vertical axis, we have the scenario where the frequencies of the two waves are the same. So somewhat loosely speaking, we call the frequency the fact that the frequency or the wavelength being identical as the same color, whereas the second option is different frequencies or colors for the two waves. Okay. Now, coherence, I said, corresponds to interference being visible or measurable by whatever be your detector, the human eye or any other. So we have essentially a visible interference only in the one condition, the sweet spot on this table, where the two interfering waves have the same polarization and also the same frequency. Only then is the summed up irradiance going to contain this all important interference term, the cross term containing E1 and E2 or E1 and E2 star. In all other cases, if either you have the polarizations to be perpendicular to each other, or even if you have the polarizations to be same or parallel, if the frequencies of the two interfering waves are different, then we are done for. We don't observe interference. Okay, so this is a notion which will again and again manifest in this course. If we get the polarizations and frequencies right, we can create scenarios where we can see these so-called interference fringes. I'm immediately jumping onto a scenario where these dark, bright alternating fringes are indeed even circular. Why not? Right? So we have a dark fringe here, we have a bright fringe here, we have a dark, we have a bright. But of course, here you see a range of colors close to the bright fringe, which we also dwelt upon a bit in the previous lecture. That was the Newton's rings. We can create these two coherent superposing beams using this Fizeau wedge. In this case, the fringes would have turned out to be linear stripes of dark and alternating dark and bright bands. Please look it up if you haven't yet encountered this. I'm sure many of you who have taken courses in optics wouldn't have missed this way of creating visible interference. The beauty of the Fizeau wedge or Newton's rings were really the fact that they were in the eras of Newton and Fizeau, when light sources were pretty much uh, more or less just naturally available light sources like the sun, or thermal sources based on like heating, I mean, a candle or something of that type. They didn't have modern lasers to create interference, nor did Young of the Young's double slit. So they were still aware of these kind of the conditions for interference and figured out scenarios where one can observe the interference. In the case of Newton's rings, of course, the this classic undergrad lab experiment, or even sometimes performed in later school, you take a flat piece of good quality glass, place it on a surface, and then on top of it place another piece of glass, which is which has a curved interface. At least one interface which is of interest here is curved. You have an incident beam which is incident on this interface. It undergoes partial reflection, then and also partial transmission. The partially transmitted wave from the first interface can or partially gets reflected from the bottom interface, and then there is a second beam resulting, which again travels upwards. So these two upward traveling beams interfere and give rise to these concentric Newton rings, and the fringes here are circular, owing to the fact that this whole experiment has a cylindrical geometry, right? You can also see different colors in the edge close to the bright regions, owing to the fact that different wavelengths close to the edge of the bright fringe going into the dark fringe essentially interfere at different angles. This is a matter of detailed calculation, which we are not going to do, but you can find a lot of material, I'm sure, on the open internet to convince yourself of this, or the optics textbooks that we have referred to. But then you don't even need to set up an idealized laboratory experiment for this. You can instead simply observe this carefully. If you look carefully enough at oil puddles where you have oil water interface films, or you have soap bubbles.